Hi, I'm Reethika Ramesh, and I'll be presenting our system VPNalyzer, which I developed with my colleagues at the University of Michigan to investigate the VPN ecosystem. Over the past decade, the fame and demand for commercial VPNs has been steadily increasing. What was once developed as an enterprise security tool has now found its way into a regular internet user's toolbox. This could be in part due to the numerous reports and news articles we see every day about internet traffic being tampered with and monitored by various threat actors. Now, we notice that VPNs are increasingly being marketed seemingly as a solution to these problems. Users have started adopting VPNs to protect themselves from surveillance, to access censored materials, to access work and university resources, especially during COVID lockdowns, among many other reasons. All of this has fueled the VPN ecosystem to grow into a multi-billion-dollar industry. And this industry, unfortunately, has a bad reputation. And understandably so, because many reports and stories have highlighted the deceptive behavior of VPN providers. But that said, it has received relatively little academic attention, with the last reliable investigation being done over 4 years ago. The previous reports and studies have all been lab-based and have used inconsistent heuristics that prevent the monitoring of important issues over time. Now, this is in part due to the large amount of manual work that is usually involved in studying VPNs. And further, these studies were limited in the scale and types of VPNs studied as well. Now, considering all of these challenges, it was clear to us that bringing transparency and better security to consumer VPNs requires a different approach. So we built VPNalyzer as a system to address these challenges in studying the VPN ecosystem. First, we wanted to create a robust test suite to rigorously test important features. And this test suite must be extensible as well, because in short, we just don't want another evaluation done by researchers 4 years down the road to start from scratch. Next, we wanted to facilitate the ease of testing for both users and researchers. We wanted to help researchers move from a lab-based manual testing environment to real-world measurement. And on the user side, they have varied threat models and use cases for VPNs, which means different types of users will prefer different VPN products. And so, crowdsourcing becomes a solution. So first, I wanted to go over a high level of our system design. A user will be able to download the tool from our website, run measurements at the click of a button, which runs our test suite containing 15 measurements. Once that is done, we get consent from the user to upload the results, which are then analyzed and displayed back to them using a uniquely generated link. So I'm sure you're wondering, how do we actually conduct these measurements? The answer is in multiple phases. So let me take the example of one of our tests to explain the different phases. Let's think about how you would detect traffic leaks that occur during a sudden tunnel failure. Conceptually, how you would test this is to create an allow list of specific hosts that are needed for the test and block all traffic except to and from the hosts on the allow list. Now, this basically causes a tunnel failure because your machine would not be able to reach the VPN server. If the VPN's leak protection is effective, the traffic to the hosts on the allow list should also be blocked. Now, while this seems straightforward, it also demands complex platform-specific implementation, which we do in 3 stages. The first of which is a bootstrap phase, which takes place when the user clicks the button to start the test. In this phase, we request administrative privileges, log the firewall state, and initiate sessions that are needed to start in the ISP phase. Next, we ask the user to turn on the VPN, and the test suite begins to run. Now, this particular test first has an initialization phase where we set up necessary components for the test, which is, of course, platform-specific. On Linux, this would look like adding new chains on the IP tables. On Windows, we log the PowerShell and the net security versions. And on macOS, we check if the PF allows us to add custom anchors. And then we enable the PF and obtain a token that is needed to reverse all changes that VPNalyzer makes. We then log the firewall state again before we make any changes. And next, we create an allow list that I mentioned before and add the hosts that we will need for the detection of the leaks alone. For this talk, I will just focus on the RipeStat data API endpoint, to which we will send a what's my IP data call. Once we create the allow list by resolving all the domains, we modify the firewall, apply our custom rules to induce tunnel failure without resetting any of the existing rules. And we log the firewall state again. Now, once our rules are applied, it would block all traffic to and from all of the hosts that are not on the allow list, meaning there can be no communication to and from the VPN server. So we can finally move on to the detection. We conduct the leak detection measurement for 120 seconds, which ensures that there's more than enough time for the VPN application to diagnose and act upon the tunnel failure. Now, to detect any possible leak, we periodically query the RipeStat data API with the what's my IP data call on both the IPv4 and IPv6. Now, if a data leak protection exists, the queries will all time out. But if there's no data leak protection from the VPN provider, the query will go through the ISP and then reach the endpoint, and that endpoint would return the user's ISP IP, which is the case that is depicted in the figure below. Now, I want to mention that we take another step here to validate our results in case the VPN is governed by a stateful firewall on the user's machine. And so for more details about this, please refer to our paper. Now, finally, going back to the phases, once the test using the VPN system, we ask the user to turn off the VPN and run the test suite again. In this test, that would just mean logging the firewall state. Now, this is the generalized workflow for an experiment. When the user starts a test, we first do all the bootstrapping via the ISP, and then we ask the user to turn on the VPN, which would run the whole test suite of the measurements sequentially. And then we notify the user to turn off the VPN, which would then run all the relevant measurements again on the ISP connection. We conduct this process in 3 stages and run the same test from the VPN and the ISP because it's necessary to do so to confirm and corroborate our observations. Now, new tests can be added easily to the test suite as long as it can work in these 3 stages. So at the moment, the tool contains 15 measurements, which we divide into 3 main umbrellas. We test various aspects of service, we test for misconfigurations and leakages, and some security and privacy essentials. Now, after developing the tool, we put VPNalyzer in practice to evaluate the current state of the VPN ecosystem. To that end, we tested 80 popular VPN products ourselves, and we found several previously unreported findings, which I'll talk about a few of the findings here today. One of the biggest issues we found was traffic leakages. First, we found that not only is IPv6 support by VPNs pretty low, 5 VPNs even leak IPv6 traffic by allowing the traffic to go through the ISP directly. Even our university VPN was one of them. We reported this to them and saw that it was fixed. Now, alarmingly, when we measured the traffic leakages during the tunnel failure using the measurement I just described, we found that 26 VPN providers leak traffic to the user's ISP upon tunnel failure in their default out-of-the-box configuration, where we don't turn on any additional security features. Now, this is especially worrying because such a tunnel failure can be induced by any motivated network operators and ISPs. And in that case, 18 of these VPNs would simply leak all traffic, and 8 of them leak DNS traffic alone, possibly in an attempt to facilitate reconnection, but that still results in users' DNS queries being leaked to the ISP at that time. Now, we went another step further and tested VPN providers in a more custom secure setting by turning on all of the relevant security settings available on the VPN application. We found that 10 VPNs still leaked traffic upon tunnel failure. Though this feature is called different things by different VPN providers, we saw that 6 out of the 10 had the recognizable kill switch feature enabled. Now, we filed responsible disclosures regarding our findings with the relevant VPN providers for all of these. And when we were doing our testing, we also found that 2 VPNs were configured in such a way that they only acted upon browser traffic, and importantly, did not mention this explicitly when we turn it on. And next, we found that the support for certain security and privacy features that we measured is not uniform across VPN providers. For instance, DNS resolvers belonging to only 54 providers support DNSSEC validation, and only 26 support query name minimization. Moreover, we found that 14 VPNs use the Mozilla Canary domain to turn off DNS over HTTPS for Firefox users that get this feature enabled by default. We specifically measured this, and we report this because Mozilla rolled out DOH by default for its users in the US, and VPNs turning this off silently without notifying users creates a potential mismatched expectation of privacy. We contacted providers that did this, and the answer we get most often is that users can still opt into this feature by going to Firefox, and that VPNs conduct DNS filtering or that it hinders VPN performance. But again, since users are not notified about this, they will not be able to take steps to remediate it if they need to. And importantly, they may be expecting a certain guarantee while using Mozilla Firefox, which has now been silently turned off. Now, there are many more findings, which you will find in detail in our paper. But apart from these findings, we also took several efforts towards our ultimate goal of making investigation of VPNs easier and helping users make more informed choices. To that end, we worked with Consumer Reports Digital Lab, and they used our VPNalyzer tool as the first in a line of different investigations to provide recommendations to their users. Now, this also served as the first real-world evaluation of our tool. We're launching the beta version of our tool on our website during NDSS, so you should be able to download and test it out. Our ideas for the future are focused on our ultimate goal of improving the VPN ecosystem by leveraging crowdsourcing. In this paper, our findings already shed light on the lack of standardization and regulation by highlighting that various security features are turned off by default, and that the non-standard jargon that VPN providers use to refer to these features makes it more difficult for users to find and utilize them. Now, finally, we hope that our system VPNalyzer benefits researchers and users alike, and that the disclosures we filed ultimately help make the VPN ecosystem more secure. Thank you.